Hey folks, let's do some awesome stuff with Debug. Remember Debug? Remember this? This was the real proper user interface. This was like how you actually used a computer 30 years ago. This was the best user interface ever, man. I don't know why they got rid of this because this was way better than before these graphics came along and ruined everything. This was the best way to use a computer. Anyway, let's do some fun stuff with debug and show how to do some things with interrupts in on a PC, because why not? So, if you've ever done any assembly language programming, you probably know about interrupts. Interrupts means the term means a few different things. There are hardware interrupts, which are triggered usually by a pin on a chip, like the IBM PC has 16 IRQs, which are normally triggered by a hardware input. But I'm not talking about that. I'm talking about software interrupts provided by the BIOS and by the operating system. Excuse me. If you did some programming in DOS, you probably remember interrupt 21, for example, which is basically the Swiss Army knife of DOS. It's basically the general purpose. API provided by MS-DOS and also PC-DOS back in the day. And if you've ever wondered where the interrupts are, like how do you look at what the interrupts do, or how do you look at interrupt code? Well, that's a great question, and the easiest way to do it probably is to look at the interrupt table. So what you're seeing here, at the very beginning of the computer's memory, literally from byte 0, you see I did a dump from byte 0. Beginning from byte 0, the very first byte in the PC's memory, is this. This is what's called the interrupt vector table, or IVT. I think on Intel x86 processors, it can also be called the interrupt process table or something like that, or IPT. But I mean, the more general term is IVT, interrupt vector table. And what this is nothing other than a big bunch of pointers. The interrupt vector table is actually 256 pointers, each of them 4 bytes. So you have a total of 1024 bytes in the interrupt vector table. And yeah, each of these is just a 4-byte pointer to each of the interrupts that's available. You can have a maximum of 256 interrupts, and these are pointers to all of them. So for example, beginning right here, right from the beginning here, these 4 bytes from the EA all the way to the 02 there, these 4 bytes are the that's the memory location of interrupt 0, which I believe is used for divide by 0, isn't it? I don't know, I might be wrong, but I think interrupt 0 was divide by 0. So yeah, this is the memory location of that interrupt. You want to see what's in the interrupt? Look at this memory location. You'll see the code for the interrupt right there. So there are a few ways to get I guess there are a few ways to work with interrupts. I think what you're supposed to do probably is there is a DOS interrupt there's actually a subfunction of interrupt 21 in DOS to give you the memory location of an interrupt. So if we start doing some assembling here, I'll just go ahead and start typing in some assembly language opcodes here. What you want to do then is call function number 35 of int21. You set which int21 function you want from AH. Remember, int21 is the kind of the Swiss Army knife of DOS. That's kind of where the whole DOS API functionality comes from. So you choose which function you want from int21 by setting it in. You set the function you want in AH. So I'm setting AH here to 35. That tells me you want. That tells the computer you want int21 35. And what is function 35? It's basically, this is the function to get the address of an interrupt. So then you need to set in AL, you need to set which interrupt you want to use. Here for this exercise, I'm going to be working with the video interrupt. The video interrupt is interesting because it works with the video. It works with the display. It shows you, well, it doesn't necessarily show you anything, but it contacts the video BIOS and does all kinds of cool and wild stuff with the video card, with the video adapter in your computer, in your PC. So I'll go ahead and set AL to 10. That tells the interrupt that, and then I'll call in 21. So yeah, so this is just 3 lines of code, right? So the first line tells int21 that you want to get the vector of an interrupt. The second line tells int21 which interrupt you want to get the vector for, and then the third line just runs int21, which is basically a function. It's like a function call in DOS, right? So there you go, done. So if I do a dump now, yeah, there he goes. That's so you can see the instructions there. The first 6 bytes of these instructions are, or the first 6 bytes of this dump is the machine language encoding of those 3 instructions that I just typed in. So now we just want to run this. So how do we run this? We want to make sure that our registers are correct. So the code segment, yeah. So CS is 1142. That's where the computer will currently run code from. And the IP is already 100. The IP is, of course, the instruction pointer where the computer is going to start running instructions from. So those are already correctly set. 1142:100 is the location where instructions are. So I don't need, otherwise I would need to, if those were wrong, I would need to set CS and IP to actually point to where I want where these instructions are, but they're already correct. So I guess I can just, yeah, just start doing a trace. So I'll just type T to trace into these instructions. And you can see here what's happening. So it's already run that instruction move AH35. And if you look here, you can see AX, for those who don't know, AX is a 16-bit register, which is actually 2 8-bit registers glommed together. So the first 2 characters here are actually AH, and the second 2 characters are AL. And collectively they make AX. So AH has been set to 35 as requested. Now if you do another trace, we're going to see, yep, AL became 10 as requested. So now we're all ready to run int21, and this down here shows us that the next thing that's going to run is int21. So let's go ahead and do a T, and look at what happens. Okay, all this garbage down here, we don't need to care about this. These are just random instructions that are still in memory, so just forget that. But the important thing here is after you've run int2135, as we've just done, ES and BX will point to the location of the or should, hold on, what? Did something go wrong here? Because, as far as I ES and BX did not change. That's problematic. Why did they not change? Normally what's supposed to happen is, oh, you know why? Oh, I see. int21's not finished because I'm doing a T. I should probably do a P. You know what? Let's the reason why ES and BX haven't updated is because int21 is still running. This is actually the code of int21 that we're seeing here. Okay, that's the problem. Can I do a P now, or am I too late? I think I might be too late. Well, I mean, we can just keep stepping through this and wait for ES and BX to change, but we might have to wait a while. Could be a long wait, depending on okay, why did it freeze now? Okay, can I get out of this? No, I don't think I can. Okay, well, that was unfortunate. Can I reboot this, I wonder? Is there a way to reboot this emulator that I'm using here? This is not using DOSBox. This is actually using something called PCE, PC Emulator. And I bungled it up because actually, I don't even know how I bungled it up because it shouldn't... I don't know why it hung on call 1580. All right, let me see if I can close this and restart it. There we go. Okay, it's restarting again. Let's see if I can do that better this time without messing things up. Yes, indeed. This is AT&T MS-DOS 3.30A. It's pretty awesome. All right, so let's go ahead and try that again. So what did I do? I wrote a small assembly language program where I said, right, move H 35, move AL 10, and then int 21. That was it, right? And the registers normally are automatically set to your current code location. Yeah, so okay, so everything's fine. So let's just go ahead and do a P this time. So yeah, so AX gets H gets set, AL gets set, and then if I do P here, does it just go right through int 21? Yeah, there we go. Okay, I needed to do a P and not a T. It's important to know when to P and when not to P. That's one of the first things that you learn when you're a child. So here we go. So here we have ES. Here you can see BX was 0000 before and ES was 1142. So ES and BX have updated now. So ES should be the segment of interrupt 10. So this is basically the result. This is what you get when you run interrupt 2135. This is what you get. This is your output, ESBX. That's the segment and offset of the interrupt that you wanted. In this case, we wanted interrupt 10. And you can check that by, again, doing a dump of location 0. I have to explicitly say 0:0, because if I just say D0, it'll just start dumping from the current segment. I have to actually specify the segment, so I have to say 00, so it actually dumps from segment 0. All right, so here we go. So where is interrupt 10? Well, because each pointer is 4 bytes long, to get the location of the interrupt you want, just multiply the interrupt number by 4. Because each pointer is 4 bytes long. So here we wanted interrupt 10, right? So 10 times 4 is 40. It's in hexadecimal, but it still applies in hexadecimal as well. 4 hexadecimal times 10 hexadecimal is 40 hexadecimal. So these 4 bytes here should be the vector of interrupt 10. And indeed they are. It's just in reverse. And this is how they're stored. This is, if you're actually going to do something like this, if you're actually going to work with this interrupt vector table, this is something important to understand. The addresses, the vectors of the interrupts, are in fact stored backwards here. So you see how it says here, for example, the segment is C000. That is correct, but it's actually stored like this. The C0 comes at the end, and then the 00 comes before that. Likewise, the offset of the function, or the offset of the interrupt, is 07B3. So then here comes the 07, and then right here at the beginning comes the B3. So these 4 bytes are actually flipped. You have to flip these 4 bytes around to get the real segment and offset of the function. So that's a bit tricky, maybe, but it works. I mean, it is correct. The result that we got in ESBX is in fact correct. So hey, it worked. Cool, awesome. Okay, so let's go ahead and try to manually run interrupt 10, not with an instruction interrupt 10. The interrupt instruction is normally CD. Like you see here's a CD, and here's another one. So here, for example, CD 21. This is actually a call to interrupt 21 in machine language. But let's not use that instruction. Let's actually manually just jump to that location in memory and see if it works. Let me quit out of debug for a second and restart it just so everything's nice and fresh and new and clean. So fresh and so clean. So what are we doing here? We want to call, we want to directly jump to interrupt 10. So once again, let's pull up the interrupt vector table. I think it's still going to be the same, right? Yeah, it doesn't, I mean, it didn't change just because I quit debug. So what do we want to do? We want to, let's see, I'll call interrupt 10, and just like interrupt 21, interrupt 10 also has various sub-functions. So when you're calling interrupt 10, you need to use AH to set the, to tell interrupt 10 what you want. So I'm going to go ahead and, hold on, let's see, let's take a look at our registers. AX is 0000. So let's go ahead and set AX to, 0013. And if we look at it again, yeah, AX. So the first the first byte of AX, like AH tells interrupt 10 what function you want. Here I'm using function 0, which is set video mode. So I'm going to set the video mode here. And then here in AL, in the second half of AX, you tell interrupt 10 what video mode do you want. And I'm going to go ahead and shoot for good old venerable VGA mode 13, the wonderful 320 by 200, 256 color video mode that everybody loved from the DOS days. Everybody loves DOS games in VGA mode 13, right? So AX being 0013 tells interrupt 10 you want to set the video mode, that's the 00, and you want to set it to mode 13. Simple, right? So now I need to make sure that, hold on, I need to, since we want to run code, yeah, I'm going to run some code, so I need to set CS, the code segment, and IP, the instruction pointer, to point where that code is. So let's look here in the interrupt table, and we see, remember this is in reverse, so CS, the code segment, should be C000. So I'm going to go ahead and say RCS, set it to C000. And then what do we want the instruction pointer to be? The instruction pointer should be 07B3. So RIP for instruction pointer, set instruction pointer to 07B3. Is that right? Let's check this one more time. Hold on, let me just dump all this one more time just to make sure that I didn't goof somehow, because you can see it's very easy to goof when you're doing stuff like this if you don't know what you're doing, or even if you do. These are the bytes. So, right, so the segment should be C000, and indeed, code segment is C000, good. And instruction pointer should be 07B3, and indeed it is. So, okay, let's go ahead and, if I just start doing T, if I just start doing a trace, we're actually going to trace into interrupt 10. We're actually going to see the code of interrupt 10. So it starts off by doing a comparison of AH. It wants to see what AH is. It tries to guess what function you might be calling. So let's step through this a bit. Okay, we've got a no operation. Then it does a jump. Right, CLD, it clears the, what is that? The decimal? It's clearing some processor flag. Here on the right, you can actually see the flags. Did a flag change here? I don't see that any of these changed unless I'm missing something. But anyway, so all right, now it does the big push. So it's pushing. This is typical of an interrupt. When an interrupt starts, typically an interrupt pushes all the registers onto the stack so that it doesn't so that the processor doesn't lose what it had, so we can pop those back off the stack later when the interrupt is done. So yeah, so it pushes a bunch of stuff onto the stack. It pushes everything onto the stack pretty much, and then does a shift left of AH. Okay, does some so basically I guess it zeroes out AH and then whatever XOR. Okay, I'm not going to analyze all these in any great detail, but you know what I should probably do is just. Should have probably done a P, because this is actually showing everything. I mean, this is actually the code of interrupt 10. So if you want to see what interrupt 10 is doing, here you go. You got it. You can see exactly what it is doing. But I guess this is, yeah, this wasn't actually what I meant to do, but yeah, and it appears to have crashed again. Can I cannot seem to get out of this. Okay. All right. I should do less T and more P. Let me close this again and restart it once more. Yeah, I'm going to do a P this time instead of a T because for some reason it seems to crash when you do too much tracing. So I'm just going to do a straight P. So what did I do? I guess I should wait for it to finish booting before okay, here we go. So let's go ahead and run debug again. So what I wanted was right, offset of interrupt 10. So I need to set code segment to C000 and then the instruction pointer IP to 07B3. Do a quick double check. CS should be C000. Yes, it is. IP should be 07B3. Yes, it is. Seems legit. Okay, let's do a P this time. So yeah, we still see some of this stuff, but I think it's gonna skip because P normally skips calls. It normally skips subroutines. So this should work. It worked when I tested it last time. Just have to do P several times until suddenly, sometime. Come on. Are you going to crash on me again? There we go. Whoa. What happened to all my text? Okay, it clearly is not properly compensating for... You can see that the video mode changed because this one character is huge now. It's definitely changed the size of the console text. Last time I did this, though, some text remained on the screen. Unfortunately, you can't really see any text. There's just that blinking cursor in the upper left. So that's not quite as impressive as I was hoping it would be, but oh well. But the video mode definitely changed. You can't see because the video is constrained to a certain resolution. But this window that this is running in just became like about twice as big as it was before. So it definitely changed the video mode. It just didn't do it in quite the way that I was expecting. But okay, but there you go. We manually called interrupt 10 by jumping right to the memory location of it instead of normally calling the interrupt. We jumped right to the memory location of that interrupt. That's how you call an interrupt directly. That's how you call an interrupt if you don't have DOS. If you are programming in operating system less mode where you don't have any kind of DOS or any kind of OS running, then you just go to the interrupt vector table, you get the vector from there, you jump to it, and boom, your BIOS interrupt function runs just like this. We just called the video function to set the video mode, and it worked. So that's how you do it. Fun stuff, right? Okay, I'm go ahead and stop here for now. I hope this was interesting for someone. I'd be interested to get some feedback from people and see what or hear what people think. Did you actually like this? Do you think it was interesting at all? Was this of any value whatsoever? I think it's really cool. I think this kind of stuff is really awesome and interesting and exciting, but maybe other people don't feel quite the same way. So anyway, feedback is welcome. Doing stuff with Debug. It's awesome. All right, I am going to go ahead and check out for now. Thanks for watching, everyone, and I'll talk to you later. Bye-bye.